Carbon cycle. All right, here we are, guys. So we're in a perfect world and we were in the classroom together. I would have you play this game today where you are pretending to be a carbon particle and you go to one of the places of the room that represent either atmosphere, plant or animal, soil, surface ocean, deep ocean, marine life, ocean sediment, or fossil fuel. So one of those places. Let's say you start at something like marine life. Then you roll that die. It will probably tell you go to ocean sediment. As ocean sediment, then maybe you become a fossil fuel. And then you're at the fossil fuel station. You roll the die and it tells you are still a fossil fuel. You roll a die again, it tells you you're still a fossil fuel. And you roll it again, it tells you you're still a fossil fuel. Here's the deal. At that point in the game, every time you're at fossil fuel, you will always roll fossil fuel again. And then anyway, we move to the second part of the game. I switch out some of the dice. And this time, let's say you started as marine life. You roll it. Maybe you get to deep ocean. From deep ocean, you become ocean sediment. From ocean sediment, maybe you become fossil fuel. Well, this time you're like, sweet, I'm at fossil fuel. I have to go anywhere else, man. Then you roll the die and, oh, it goes to atmosphere. Because at this point, most of the time you are a fossil fuel, you roll the die, you will then end up as atmosphere. Now from atmosphere, you might stay in the atmosphere. You might actually be more likely to end up then as either plant or animal or surface ocean, and the cycle starts again and again. And then when you're done, I have you take a look at the data. This is data from all of the students of mine that have ever played this game. What we have here is the results from the game part 1. And this one is, for instance, where, you got stuck in fossil fuel, you stayed as fossil fuel. And you can see that gray chunk is the biggest chunk of the pie. So pre-year 1800 or pre-1800s, most of the carbon on this planet was stored as fossil fuel. After that, there was a good chunk in the atmosphere and a good chunk in the surface ocean, and after that, deep ocean. Okay, so that's where most of the carbon was. Now, the second part of the game we were playing was representative of carbon after the 1800s. We'll take a look at the fossil fuel sliver of the pie there. It's definitely a sliver. I mean, if this is a pie, you are getting shafted. You are not getting a whole lot. So there was just not as much carbon as fossil fuel at that point in time. Take a look here at the atmosphere. That is a huge chunk of the pie. Most of the carbon is in the atmosphere. I mean, take a look at this. Before, meh. After, whoa. There's also a lot more in the surface ocean. This is after the 1800s. We're about 20% in the surface ocean, where before we were only about 15%. So there's more in the surface oceans as well. Well, okay, so take this back to the class notes that you're looking at. We're talking about where the carbon is and, whether or not something, I'm just going to skip that part. You guys, I'm guessing, don't care. Okay, so some things to understand. These parts of the atmosphere, these parts of the Earth system where you're rolling the dice, some of these are part of the quick carbon cycle, things where the carbon stays there for 1 to 5 years, maybe less. I mean, think about like a land animal. You are considered in this context a land animal. You can breathe in and then breathe back out carbon in a matter of a few minutes or seconds even, honestly. So that would be less than 1 year. But anyway, 1 to 5 years on average. That could also be like the time a plant has carbon in it, the plant dies, the plant decomposes, and it becomes soil. I mean, that might take as much as like 50, or like a tree that lasts a really long time, maybe as much as like 100 years. But even still, that's part of the quick carbon cycle. Slow carbon cycle. These are places where the carbon hangs out for a really long time. That would be deep ocean, ocean sediments, and fossil fuels. These are thousands to millions, sometimes billions of years. And then soil, you'll notice, is on both lists. Soil, carbon can come and go from soil, surface soils in particular, very quickly. Some of the deeper soils, carbon can be there for a very long time. And actually, those soils can eventually form something like fossil fuels. So that is the natural where the carbon is and everything. So that's what's going on pre-1800, where most of the carbon is in fossil fuels and a good chunk in the atmosphere and a good chunk in the oceans, the surface oceans. After the 1800s, most of it is in the atmosphere. There's very little here in fossil fuels. Well, what's the big difference? What happened? And here's the part of class where you guys impress me that you tend to know human history better than I do. But this was the Industrial Revolution in the 1800s, like mid-1800s, where that is where humans started to burn fossil fuels. So what we're doing is we're taking those fossil fuels from over here and very quickly releasing them to the atmosphere. So that's how we end up now with such a small chunk of carbon in fossil fuels and the bulk of it in the atmosphere. Now, as something we have previously discussed, and I want to make sure you remember this, a lot of then once the carbon is in the atmosphere through diffusion that we talked about, it ends up in the surface ocean, and we have the ocean acidification. We recently learned about this like a week or two ago. So ocean acidification, the surface ocean absorbs a lot of that atmospheric carbon. So that carbon we're pumping into the atmosphere, the ocean absorbs it for us. But that's not really a good thing. I mean, yeah, it's taking it out of the atmosphere, but we have all those issues that we have going on in the surface ocean. Now, okay, I want to just show you some more data relating to all of this. This data that I'm showing you comes from climate.nasa.gov. That is probably my favorite website, period, but it's certainly my favorite website with information about climate change and like how we know. And you know what, just check out the website. Just click the link. Just click the link and go there. But here's some of the stuff we see from that website. First of all, global temperature rise. This is the average global temperature in a year. Now, if we look at this, you'll see that these gray circles are like up and down, up and down, up and down. That's seasonal variation. The black line is the average of those annual variations. Then I drew this red line in here, just kind of showing you the general trend since the late 1800s. The general trend is that the temperature has been rising. Then there's this graph. This graph that we're looking at is carbon dioxide level in parts per million. And this goes back 400,000 years of sampling of carbon dioxide data. Now, we know that, by the way, because these gases had been trapped in Antarctic ice cores, and we can harvest that, much like we harvest like the rings of a tree. We can harvest these ice cores and the samples of air trapped in there. Anyway, so we can see the levels of carbon dioxide have risen and fallen over the last 400,000 years, and it's about like 100,000 years between spikes in carbon dioxide. Now, previous to now, the atmosphere had never breached 300 parts per million of carbon dioxide. Well, here we are in like 1950, and from 1950 to present, look how sharply that line is going up. Furthermore, look how high that line is above the normal rise and fall of carbon dioxide. So 400,000 years of normal rises and falls of carbon dioxide, then zoom, bam, Industrial Revolution happened. And the amount of carbon dioxide in our atmosphere is a lot more, like 2 to 4 times more, well, 2.5 to 3.5 times more than it ever was in previous modern history. And I am referring to 400 years ago as modern history. So take that as a relative piece of information. Anyhow, so here's some data that's pretty much showing you, yep, temperature has risen. Also, carbon dioxide levels have risen. Now, that in itself could be unrelated, but guys, we have previously looked at this data where we know that carbon dioxide heats up more than the air. And from that, we had this logical deduction that if the Earth's atmosphere has more carbon dioxide, then the atmosphere becomes warmer. Okay, So pairing that with what we are seeing here, dun 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 dun, putting that all together, what we get is anthropogenic climate change. We have learned the anthropogenic word before, but what that means is genic as in generate, made by, anthro as in anthropology, refers to people, man-made climate change. What's happening on Earth right now is not the natural norms.